In this video, we're going to learn about a different differentiation technique called implicit differentiation. Now, implicit differentiation is used when you have a function that is defined implicitly rather than explicitly. Most of what we've been working with has been explicit functions. That's where you have y equals something with a bunch of x's in it. An implicit function is when you have x's and y's all mixed up together in the equation. It doesn't just say y equals something with x's. Then y can still be considered a function of x. It's just not solved explicitly to be in terms of x at that point. Now, we can still find the derivative of y with respect to x without solving for y first. The way we do that is this technique called implicit differentiation. So I'm going to write down our steps and then we're going to do some examples. So steps for implicit differentiation. First, you are going to differentiate both sides of your equation. When you differentiate both sides of the equation, every single time you take a derivative of a term that involves y, you have to multiply by dy dx. This is the weird part of implicit differentiation when students are learning it. You can multiply by dy dx or y prime, depending on which notation you're using. And then step 3 is to solve for dy dx or y prime by isolating it on one side of the equation. So the important step really is step number 2. Why are we multiplying by dy dx or y prime when we take a derivative of a y term? What this is actually the chain rule that we just learned about. Y is a function of x. We just don't know what y is. So when you take the derivative of the y's, that's like the derivative of the outside function. And when you multiply by dy dx, that's representing multiplying by the derivative of the inside function. It's just that we don't know exactly what that derivative is. We will solve for that in step 3. So this really is still our chain rule. It's just kind of messed up. So let's go ahead and just do a bunch of examples because it's the best way to learn how to do this. So first, we're going to find dy dx when x squared plus y squared is equal to 25. So that equation, x squared plus y squared equals 25, is an equation of a circle. It's not a function, but we can think of it as two different functions, but put together in the same graph. So this dy dx is still going to represent the slope of tangent lines to this circle at any possible point. But to get this dy dx, we're going to have to use this implicit differentiation. So let me rewrite my equation. And implicit differentiation, again, just says take the derivative of both sides. Use all of the rules we already know. The only thing that's different is when you take a derivative of something involving y, you need to multiply by dy dx or y prime. I'm using dy dx in this problem because that's the way it was stated. So if I take the derivative of x squared, we get 2x. When I take the derivative of y squared, you're going to want to say it's 2y, but we are doing implicit differentiation and I need to multiply by dy dx. And then don't forget to take the derivative of the right side of the equation. Derivative of 25 is 0. So what we did here was differentiate both sides, and that got us this result. Now I can solve this equation for dy dx. I can do that by moving the 2x to the other side. And then dividing by the 2y. And I get that the derivative of y with respect to x is equal to negative x over y, because my 2's cancel out. And that's all there is to it. So implicit differentiation sounds a lot scarier than it actually is. The only thing you have to remember is to make sure you multiply by dy dx whenever you're taking the derivative of a y term. All right, so let me erase some of this. Next example, find the equation of the tangent line to the circle x squared plus y squared equals 25 at the point 3, 4. So, equation of a tangent line. You know the slope of the tangent line is going to be the derivative evaluated at that point. That's why I didn't erase this last bit. This is the same circle from the last problem. We already know dy dx is negative x over y. So that means I can write that my slope is equal to my dy dx, which is negative x over y. But at that point, we get that my slope is negative 3 over 4. So that's the slope of my tangent line. And now I can just use point slope form to write the equation of my line. Y minus 4 equals my slope times x minus 3. And this is the equation of the tangent line to that circle at that point, if I keep it in point slope form. Or if I put it in slope intercept form, you'll get y equals negative 3/4 x plus 25 over 4. Either way is fine. And that's not too bad. So the point of this problem is that you can write equations of tangent lines to implicit curves as well. You just have to use implicit differentiation to find the slope of the tangent line. Let's do another example. Find the equation of the tangent line to the curve x to the third plus y to the third equals 6xy at the point 3, 3. So this time we're going to have to do the implicit differentiation and then write the equation. So I need to first find my derivative by using implicit differentiation. This time I'm going to use the prime notation just so you can see it both ways. It does not matter if you use dy dx or y prime, they're the same exact thing. So first thing we need to do is we take our equation and we have to differentiate both sides. This one is a little bit trickier because of the right side of the equation. On the left side though, I'm going to get 3x squared. Derivative of y to the third is 3y squared, and don't forget your dy dx or your y prime, and I'll use y prime this time. And then this derivative of the right side is a little bit trickier, and the reason for that is we have a product rule. I have a 6x times a y. So I have to do a product rule on that right side. The product rule says that it's going to be the first guy times the derivative of the second guy, plus the second guy times the derivative of the first. So let's do this derivative of the y. Derivative of y, we would normally think is just 1, but we have to multiply it by y prime, so I get y prime. Derivative of my second guy is 6. So now I have this lovely equation. Let me rewrite it a little bit. We have 3x squared plus 3y squared y prime equals 6xy prime plus 6y. And I want to figure out what y prime is. So we need to get the y prime terms all on one side of the equation and everything else on the other side. I'm going to move this 6xy prime over to the left and move this 3x squared over to the right. So when I do that, I get 3y squared y prime minus 6x y prime equals 6y minus 3x squared. And now on this left side, I can factor out my y prime, leaving 3y squared minus 6x. So to get y prime completely by itself, I just have to divide by 3y squared minus 6x. And I get that my derivative is 6y minus 3x squared over 3y squared minus 6x. This can simplify a little bit. I can factor a 3 out of both the numerator and the denominator and cancel that like factor. So if I do cancel my like factor of 3, I will get the simplified version, which is y prime equals 2y minus x squared over y squared minus 2x. There is my derivative. So this derivative is what's going to give me the slope of my tangent line. The point that we were supposed to be using was the point 3,3. So at the point 3,3, my derivative is equal to 2 times 3 minus 3 squared over 3 squared minus 2 times 3. So I get 6 minus 9, which is negative 3, over 9 minus 6, which is positive 3. So I get negative 1 when I simplify. This is my slope. So to write the entire equation of that tangent line, using my point slope form, I get y minus my y1, which is 3, equals my slope times x minus x1, which is also 3. Or if I put it into slope-intercept form, we get y equals negative x plus 6. And there we go. Let's do one more example where we just have to find the derivative using implicit differentiation. And then we're going to move on to an example where we have to actually find a second derivative using implicit differentiation. But first, let's just do a normal implicit problem again. So we're going to find dy dx if sine of x plus y is equal to y squared times cosine of x. This one is a little bit more complicated because we're going to need, along with implicit differentiation, we're going to need a chain rule and we're going to need a product rule. So let me rewrite my problem. Sine of x plus y equals y squared times cosine of x. And then I'm going to differentiate both sides. On this left side, I have a chain rule. I have sine of a bunch of stuff. So the derivative of the outside function is cosine of that stuff. And the derivative of the inside function, derivative of x is 1. Derivative of y would be 1, but times my dy dx. So this was a chain rule. Outside, inside. And over on the right side, I have a product rule of y squared and a cosine x. Product rule says it's going to be the derivative of the first guy times the derivative of the second guy plus the second guy times the derivative of the first. So the derivative of my second guy, that's derivative of cosine x. That's negative sine x. And the derivative of my first guy, derivative of y squared is 2y, but I also need my dy dx. So that's kind of a mess. Let me quickly rewrite it and then we'll figure out what to do. So rewritten so it's a little less ugly. Cosine of x plus y times 1 plus dy dx equals negative y squared sine of x plus 2y cosine x dy dx. So this is what we have to use to try to find our dy dx. Now, just like the last problem, to find dy dx, we want all the dy dx terms on one side and everything else on the other side. The first thing I'm going to do is distribute over on this side. And when I distribute, what we get is cosine of x plus y plus cosine of x plus y times dy dx equals negative y squared sine of x plus 2y cosine x dy dx. And now I'm ready to move everything with a dy dx to one side and everything else to the other side. I'm going to bring the dy dx terms over to the left side. So I will get cosine of x plus y dy dx minus 2y cosine x dy dx equals negative y squared sine x minus cosine of x plus y. All right, so now over on this left side, I can factor out my dy dx. When I do that, I have cosine x plus y minus 2y cosine x inside the parentheses. And nothing changes on the right side. Then all I have to do to get dy dx completely by itself is divide both sides by everything in these parentheses. And I get dy dx is equal to negative y squared sine of x minus cosine of x plus y all over cosine of x plus y minus 2y cosine of x. And that is my derivative. It's kind of ugly, but it's still just following the same steps and being very careful. Make sure you're not sloppy and you'll get to the right answers on these problems. I will point out, sometimes when you do implicit differentiation problems, your answer might look similar to what it's supposed to be, but a little bit different. So if you're doing problems out of a book and you're checking the answer in the back and your answer looks slightly different, that doesn't necessarily mean you did it wrong. The answers will look different depending on whether you put the dy dx on the left side of the equation versus the right side of the equation, but they would still be equivalent answers. So just Keep that in mind. It should look similar to what an answer in the back says, but maybe the orders are flip-flopped a little bit. Usually that means you still did it correctly. If you ever doubt it, just try plugging in some values into your answer and the answer in the back of the book, and if they agree, you're probably okay. All right, so now we need to talk about how to do second derivatives using implicit differentiation. So if you're going to do a second derivative, first thing you should do is find your first derivative first. So that means do all of the implicit differentiation to find your dy dx, including solving for dy dx at the end. Then do implicit differentiation again. And you are going to substitute what you have for dy dx as needed. What I mean by that is when you do your implicit differentiation again, a lot of times you're going to get dy dx's over on one side of the equation. But from our first step, you will know what dy dx is equal to and can substitute that information in. So let's do an example where we have to do a second derivative. So example. A particle moves along the curve 8x squared plus y squared equals 8. Find an expression for the acceleration. All right, so we know that acceleration is a second derivative. So I need to find the second derivative of this implicit curve using implicit differentiation. We're going to start by finding the first derivative. So let me rewrite my problem. And we're going to differentiate both sides of the equation. Derivative of 8x squared is a power rule, 16x. Derivative of y squared is a power rule to get 2y, but you also need dy dx. Don't forget to take the derivative of 8 to get 0. So now I'm going to solve this for dy dx. I'm going to move 16x to the other side. And then I'm going to divide by 2y, which will give us negative 8x over y. That is my first derivative. To find the second derivative, we're going to have to differentiate again. So let's see here. I'm going to just put notes to myself up in this corner in red. My dy dx is negative 8x over y. And also my original equation was 8x squared plus y squared equals 8. So just in case I need that information, I'm just going to put it up in the corner so I don't lose it. All right, continuing in our problem, we want to find the acceleration, so I have to differentiate again. When I take the derivative of dy dx, that is going to get me my second derivative. And over on this right side, that's a quotient rule. So we have to do a quotient rule with implicit differentiation. My quotient rule says low d high minus high d low, square the bottom, and away we go. So the derivative of the top is derivative of negative 8x. That's negative 8. Derivative of the bottom is the derivative of y. That is dy dx. So let me quickly rewrite this. I have d squared y over dx squared, or my second derivative. That is equal to negative 8y plus 8x dy dx all over y squared. Now, we can simplify this because we know what dy dx is. So this dy dx right here, I can replace that with negative 8x over y, exactly what dy dx is equal to. So when I replace that dy dx with what it's equal to, I get that my second derivative is equal to negative 8y plus 8x times my dy dx, which is negative 8x over y squared. And we can simplify this even more. If I multiply both the top and the bottom by y to get rid of this extra fraction up here, I'm going to get negative 8y squared minus 64x squared all over y to the third. So in case you needed that step, I'm just going to write a little note here. I'm multiplying the entire fraction by y over y to get this result. And now let's just factor out a common factor from the top and just see what happens. Something I notice is in the numerator, I can factor out a negative 8. Both of my terms in the numerator have a negative 8 in common. So I would get y squared plus 8x squared inside those parentheses. Now, why did I do that? Well, just take a look at what's in the parentheses there. I have y squared plus 8x squared. Do we know what that's equal to? This y squared plus 8x squared is back to my original equation. We know 8x squared plus y squared is 8. So y squared plus 8x squared is also 8. So when I plug in that information up there, we get that my second derivative is equal to negative 8 times 8 over y to the third, which when I actually multiply those together, we get negative 64 over y to the third. And that is an expression for the acceleration of that particle. All right. So that wasn't too terrible. That was actually all right. And that is all there is to implicit differentiation. It's really not any different than our regular differentiation. It's just that now we can take derivatives without having y by itself first. We would just use implicit differentiation, which is honestly just a fancy chain rule. If you have questions, feel free to drop them below, or if you're one of my current students, you can ask an email or in office hours, and I'd be happy to help. I will see you guys in the next video.